Well, hello there. So this lecture is going to be covering node voltage analysis. This is one of the big topics for the class. We'll be using this for the rest of the semester. So hopefully you will get some good habits and learn this and practice it and get good at it and efficient at it, because it will be useful all the way through the rest of the semester. So this lecture is based on our textbook in chapter 3. So feel free to refer there, and I'll be using their steps for this process. So these are the steps as laid out in the book for doing node analysis. They have 3 steps. What we're solving for are node voltages. So you know what a node is, and we'll select a ground node so that we can have a reference voltage, and then we'll be solving for all of the node voltages in the rest of the circuit. So we get all of the voltages with one analysis. So the steps are identifying the nodes and labeling them if they're known or unknown voltages. And then for each of the nodes with an unknown voltage, we use a combination of Kirchhoffs Current Law and then also Ohm's Law to analyze each node. And then we will get an equation for each node with an unknown voltage. So if there are 4 unknown voltages, we'll get 4 equations, and we'll solve those as a system of equations to find the answers. So this lecture is going to start with a simple example going through the steps. Then the next lecture has a little more complicated examples, and we'll build on it. But by the end of this module, you should have seen most of the tricks and applications of node analysis. So here are our steps again, step 1, steps 2, and step 3. Step 2 is the one that has the most parts and work to it. And so here in step 2, we are using Kirchhoffs Current Law at each node with an unknown voltage, and also Ohm's Law to get our system of equations. And so there's a little more detail. The book references this KCL template, which we see over here. And so this is sort of a cheat sheet or a cookbook of a node with 3 resistors and a current source connected to it. And you can see this is what you should do. You should draw a picture of each node. You should label the currents in each branch connected to the node. Current sources are already labeled, but the other ones need to be labeled. That way you can easily do Kirchhoffs Current Law at that node. And then the next step, once you do Kirchhoffs Current Law, is to use Ohm's Law to replace the currents with an equation that's in terms of voltages, because we're solving for the voltages. So it's always Kirchhoffs Current Law and then Ohm's Law. Ohm's Law here is with the node voltages. So we have an arrow that we've drawn showing the current direction. So that's why we need to draw all of these little arrows. And then the way I remember how to write the Ohm's Law with nodes is it's the tail voltage minus the head voltage is what goes divided by R. So here's a little picture of a resistor with a node at each end, VA at one end and VB at the other end, and the current I going into node B and coming out of node A. And so if we want to write I in terms of Ohm's Law, I is V over R, but it's the voltage difference, and so it's always the tail voltage, VA, minus the head voltage. So the tail of the arrow is over here, the head of the arrow is over here. That's what I'm talking about. This arrow's got an arrowhead on it. So we subtract the arrowhead voltage from the arrow's tail voltage and divide by R. So in this class, we're generally going to write all of the currents going out. So the tail voltage will be our unknown, our node voltage in almost every case for this class. But this is the correct implementation of the Ohm's Law sign convention, however you do it. You can see we have current sources in our circuits, and we'll have voltage sources too. Current sources just come into Kirchhoffs Current Law as the known current. If it's 3 amps, it's 3 amps. So write that in. Make sure you get the sign correct on that. Voltage sources will either make our analysis easier by removing an unknown, because the voltage source can just define a voltage at a node, or it will make it harder. It's not super hard, but a little bit harder, and we'll use a thing called a supernode for the voltage sources that aren't connected to ground. So So those are all farther down. We're going to do a simple example first, just to get going. So here's our simple example. It's the familiar voltage divider. So if you see this, you don't really have to analyze it because we know we've already done the analysis, and so we should be able to check the answer. But this one is a good one because it's got just 3 nodes. There's a node here that's labeled V1. There's a node up at the top here, and the ground node down here. And so if we set this as the ground node, that's something we have to choose in our step 1, then this top node has to be Vs. So if this is 9 volts, obviously you're going to get 9 volts from here to ground. So this is where the voltage source makes things easier, because this is not an unknown node voltage, it's a known node voltage. So we have Vs up at this top node. So only one unknown, V1, right here in the middle. So we've identified the nodes. In our book, they want you to only analyze the extraordinary nodes, which have 3 or more connections. It works fine if you analyze the ordinary nodes too, so that's what we're doing in this example. But of course, we could solve this without node analysis by combining the resistors and using Ohm's law and then backing out the parameters we need. So that's why they only do the extraordinary nodes. They simplify the other ones just to reduce the number of equations. So we know there's one unknown node voltage, the V1 node, and so we use step 2 here at each of those nodes, just the one here, and we use Kirchhoffs Current Law, and then we use Ohm's Law. So the first step is, I think it's nice to draw a little picture of each node, maybe separately from the diagram, that shows the currents running out of it and labels the voltages and the resistances and everything. Sometimes you could do it on the drawing. But here we've got I1 and I2 going out. And again, you can follow this little template as a cheat sheet if you want to remember how all of this works. So I've labeled I1 and I2, and then we can use Kirchhoffs current law that says that the current going in equals the current going out. So here we have the current going out, I1 plus I2 equals nothing coming in, or the current going out equals 0. Then we have to use Ohm's law to replace the currents with voltages, so that, because we're solving for the voltages. So here, again, it's the tail voltage minus the head voltage when we're looking at this. So I1's tail is V1, tail of this arrow, and its head points all the way over to the Vs node. So I1 is V1 minus Vs, tail voltage minus head voltage divided by its resistance. And I2's tail is also V1, and its head is connected all the way down here to ground. So V1 minus 0, because the ground is always at 0 volts, divided by R2. So you can combine these in your head as you get more practice, but to start with, it's really nice to write them down and write these down. That way you'll make fewer mistakes. So we combine them together. Here's I1 plus I2 equals 0, and it's one equation and one unknown. We can solve for V1 and we get our regular voltage divider equation. So this is our third step. We have an equation like this for each node with an unknown voltage, and we solve it. Okay, so that's the simplest example. So again, this is our summary. We have the steps where we identify and label all of our nodes. Then for each node with an unknown voltage, we have an equation. So we'll have the same number of unknowns and equations. So we'll do a KCL and Ohm's law combination. And then we solve our system of equations. Remember the template for Kirchhoffs current law, which is doing Ohm's law directly. Down here is an example, and it's okay to write the steps where we add up I1 plus I2 plus I3 equals 0, and then Ohm's law. This is I1, I2, and I3. And don't forget to include current sources with the proper direction. So this I0 is coming in, so it gets a negative sign. Negative out. Negative in means out. Voltage sources we haven't done a lot with, but they're either easy or hard, as we'll see. So the next video will be some examples showing a little more how to do this, and we'll get into some details. See you in the next video.